Good morning, everyone. I am Mahidhar. Today we are presenting a research framework called DeDe, which stands for Decouple and Decompose. This work is led by Shiying Xu from Harvard University and Francis Yan from University of Illinois. Both the authors work in the field of cloud systems and large-scale resource allocation, where the goal is to efficiently distribute compute, network, and storage across many users. And this presentation explains why resource allocation is becoming so difficult at cloud scale and how DDE provides a fast and efficient solution. So this research framework is presented by Akshay Bobbala, Varshit Grandhi, MB Sushant, and Mahidhar Reddy. Coming to the abstract of this paper, uh, in modern cloud systems, company handles millions of resource allocation decisions. How many GPUs each job should get, how much bandwidth to assign, or when to migrate workloads. And traditional optimization solvers become extremely slow as the scale increases. So, the authors observed that most real world resource problems can actually be broken into smaller independent parts. Uh, and DED uses a decouple and decompose approach to take advantage of this. So it first splits one giant optimization into many small subproblems that can be solved in parallel. While still getting near optimal results. So this makes DDE applicable to many case studies like cluster scheduling, traffic engineering, and load balancing. In the cloud platforms, thousands of users submit tasks continuously, and the resources must be allocated fairly and efficiently, which is a tedious task in itself. And today's workload are huge, and the problem keeps getting bigger, and it grows very fast. Therefore, the existing commercial servers aren't able to keep up. So, the existing approaches either rely on heuristic or assumptions or machine learning. These solutions can work in certain cases, but they don't generalize well to all workloads, and many of them still take too long. So, our main goal is to find a general and scalable method that solves large allocation problems quickly. So, this is exactly what DED provides us. Coming to the challenges we face during cloud resource allocation. So the main challenge is the scalability. As the number of as the number of variables increase and the workload increases, the existing solutions are limited. As we can see, heuristics and assumptions and ML might be fast, but still they have very less reliability. Whereas you come to some modern optimization solvers like Gurobi, which are reliable, but they are not fast enough. So this creates a need for general and a scalable solution, which which can solve efficiently large scale problems when the number of variables are in millions or even more. Let's take a simple analogy to understand the problem. So, imagine you have workers, which is representing resources here, and tasks, which is representing demands. So, each worker can do some tasks better than others, which means each worker has different skill set. So, now you must assign workers to tasks to maximize the productivity while not overloading any worker, which means any resource shouldn't cross its limit, and making sure each task get enough attention, which means each demand is assigned enough resources such that it is successfully completed. So the challenge here is doing this for millions of workers and tasks is very hard for traditional solvers. Let's see why DEDE is a good solution for our problem. Many allocation problems can be separated into decision per resources. In our analogy, it's like constraints on maximum number of work hours a worker would do, and decision per demand. That is a minimum number of work hours of workers required for a task to be completed. So now, if we separate these two parts properly, we can solve them independently and in parallel. This gives a huge speed improvement while keeping solution quality high. That's why DED is needed. Let's take a real example. Uh, Clouds run on many jobs on different types of GPUs, A100, H100, V100, and so on. So each job performs differently on each GPU type and need different amounts of GPU time. So at the same time, every GPU has a fixed capacity. So the problem here is, how do we assign GPUs to the job to maximize total throughput while not violating capacity or job limits, which are the constraints? Per job demand and per GPU capacity limits must not be exceeded. Let's see why this problem is hard. So the Xij, which represents the amount of GPU time ith GPU gives for the jth task, affects both the sides. It counts towards GPU capacity and it counts towards job demands. Because every decision mixes these two constraints, the solver has to consider everything at once. So this creates entangled constraints. So, and also this becomes massive when jobs and GPUs scale up and the commercial servers really struggle. So we need fast and real-time decisions. And let's see how DD fixes it. So first we copy allocation matrix X into Z, a duplicate matrix, and separate the resources and demand constraints, and turn one big problem into two, and M resource subproblems and N demand subproblems. M resource subproblems would be applied on X and N demand subproblems would be applied on Z. So, and now we have two problems which we can solve in parallel and synchronize them using ADMM, which we would discuss in detail later. So parallel solving leads to faster and near optimal solution. So now
Let's discuss about DD. DD stands for decouple and decompose. Whenever we are solving these kind of resource allocation problems, here both the demand constraints and resource constraints are deeply intertwined. Because of this, we cannot use traditional greedy methods. Hence, we have to use DD. DD is basically an optimization framework which is made for large-scale optimization problems. And it works on the fact that these kind of resource allocation problems can be divided into two separable structures. Because of this division, decouple and decompose enables massive parallelism while producing near optimal solutions. Now let's look at some limitations of previously existing solutions to solve these optimization problems. Earlier, people used linear programming and mixed integer linear programming solvers, but these were not suitable for large-scale problems. And then came up a method called POP, which basically partitions the optimization problem into smaller subsets. But this method ignores the cross-subset dependencies. That is the reason it leads to suboptimal solutions. And then people had to come up with DD. Unlike POP, it does not ignore the entanglement between the resource constraints and demand constraints. It basically transforms the problem into alternating per resource and per demand subproblems. We'll look in the later slides what this means. The first step of decoupling is basically reformulating the original optimization problem as follows. So here the key idea is basically to create an auxiliary variable called z and copy the original allocation matrix x into it. This x and z separate both the resource constraints and demand constraints so that the newly created optimization problem is as follows, which is minimization problem of the objective function subject to both resource constraints and demand constraints. We additionally add a constraint x is equal to z, which is basically to maintain the equality between both the constraints of demand and resources. DD is based on an idea called ADMM, which stands for Alternating Direction Method of Multipliers. ADMM is basically solving a problem of the kind minimizing f of x plus g of x, which is subject to ax plus bz equal to c, which is similar to the previous reformulated problem. And ADMM is built on an augmented Lagrangian method, which basically converts constrained optimization problems into a sequence of unconstrained subproblems. This is a Lagrangian which is used to solve this optimization problem. The key mechanism here is ADMM alternates between optimizing x with z fixed and then it optimizes z with the x fixed. It repetitively iterates between these two and finally converges into an optimal solution. ADM basically works by using augmented Lagrangian. This Lagrangian contains resource utility terms, demand utility terms, and some penalty terms, which are basically consisting of dual variables of resource constraints, demand constraints, and an additional coupling constraint, which is basically x is equal to z. And ADMM basically iterates through updating x by keeping z fixed, and then it updates z by keeping x as a fixed variable. And it also updates these dual variables like alpha, beta, and lambda for coupling constraints. Now let's look at decompose. Once we are done with decoupling x constraints and z constraints, both the constraints have been separated. So now we have to update x while keeping z fixed. So x is a very large equation, and solving it is still a slow process. So we have to decompose this solving x to solve these problems parallelly. Since x update only solves for x, we can ignore all the terms which does not contain x in the Lagrangian. Now this X update has three terms, which involves separable objective, term from resource constraints, and one term from the coupling constraint, which is X is equal to Z. Now this new objective function, we can split it across the resources I. Um, so this X update function, which was previously a large function, can be split into multiple sub equations. Like if there are n resources, we can divide it into a summation of n different resource subproblems. And we can solve those subproblems parallelly and then combine them to solve this bigger problem. That's basically how decomposing works, and solving parallelly helps reduce a lot of time. Now let's see the benefits and complexity gains of using this function decompose. Why decomposition works? This decomposition works because the objective function is separable. Each resource has its own utility term f of xi. When we are updating the value of x, we can divide it into we can divide it into each of its resources, because these resources act as an independent resources, and this helps in turning the original n-by-n problem into n separable problems of size m. And the performance update advantage we get here is each of these n subproblems can be solved parallelly. Because of this, the original time complexity, which is O of n into m to the power 2.373, which is basically divided into n subproblems of time complexity O of m to the power 2.373. So this effectively helps ADMM in converging in small number of iterations. Let's look at the generality of DeDe. Here's a table which consists of the real-world resource allocation problems which can be solved using DeDe. And when it comes to variables, DeDe supports continuous variables. It also handles Boolean and integer variables via projection. When it comes to objective functions, it can handle basic objective functions along with convex objective functions and constraints. DeDe directly assumes linear constraints. Unlike POP, which relies on granular setting, like DeDe has no such limitation. DeDe is very general. Like it is suitable all the real workloads which we can see in real life situations. Limitations of DeDe. DeDe is not always an optimal approach. There are some scenarios where DeDe doesn't work really good. Let's look at those. The situations where there is limited parallelism. DeDe speed basically depends on decomposing the problem into subproblems. And if when this decomposition was fully possible, parallelism decreases. And some situations where DD is not good is where we have non-separable objectives and non-separable constraints. Let's look at some of the cases where DD is not that optimal. Suboptimal solutions. DD works on ADMM. So ADMM has some standard assumptions. When these assumptions break, DD cannot converge to optimal solutions. Let's look at those conditions. Non-convex problems. So basically, ADMM assumes convexity conditions. Whenever the objective functions becomes non-convex, the objective function like the DD cannot converge into the optimal solution. And nonlinear constraints. As we have previously discussed, DD assumes linear constraints. If there are nonlinear constraints, then we have to reformulate the problem with the help of an indicator function. But such function destroys the convexity of the objective and converts the objective into non-convex. We have already discussed that point. And it also doesn't work good when we are using higher allocation of higher dimensions. DD basically works good with 2D allocation matrix and 2-block ADMM as we have seen previously, which is optimizing both X and Z. But multi-block ADMM can suffer from convergence instability, leading to suboptimal solutions.
We will now discuss an interesting thing, case studies. We mainly study on cluster scheduling, traffic engineering, and load balancing. Now let's dive deep into this. Suppose there are 2K diverse tasks and these tasks should be done by 16K people. We should divide the tasks among the people so that the minimum throughput of any task is to be maximized. This is done by cluster scheduling. A heterogeneous cluster is a group of computers that are not identical in terms of their hardware or resources. Allocating resources such that the minimum throughput of any job to be maximized is called max-min allocation. Coming to formulas behind this. Variables. Jobs are time sliced across available resource types where Xij is the fraction of time that each job J spends on each resource type I. Our objective here is to maximize the minimum normalized effective throughput for each job. Coming to resource constraints, for each computing resource type I, the total amount of resources requested by all jobs cannot exceed the corresponding capacity. That is, sigma xij zj over j should be less than capacity of I for all I. And coming to the demand constraints, for each job j, the sum of all fractions of time must not exceed 1 naturally. That is, sigma xij of I should be less than or equals to 1 for all j. There is another variant of cluster scheduling algorithm called proportional fairness. It shares the same variables and constraints as above, except the objective changes. Here, the objective is to maximize the sum, which is the log of throughput of j comma x of j. How can DD help us to optimize cluster scheduling? As we have seen earlier that DD requires the separable nature of variables with an objective to maximize or minimize a sum with a linear constraint on each job. This is well shown by cluster scheduling. We can decompose the problem into n per job allocations and m per demand allocations. Now that we have discussed so far about DD in cluster scheduling, we would like to test it at large scale in heterogeneous cluster. 456 distinct resource types are there, and each type we randomly draw a count from 8, 16 and so on 64 and a total of 16,520 instances. Jobs arrive as a Poisson process with an inter-arrival time of 100 seconds, and we recompute allocations every 6 minutes and run 200 times, which takes approximately 20 hours. Each job requires instances belonging to 1 to 32, and 33% of jobs are restricted to specific types. And we use a Gavel simulator to simulate this, and the data is simulated using benchmarks. Comparing DD with others. DD rapidly reaches near optimal maximum allocation, which is 94% in 3 seconds and 99% in 10 seconds, shows a tremendous trade-off between allocation quality and runtime. Coming to other solvers, exact solver is very slow due to its sequential solving, whereas DD computes parallelly, so it takes less time to compute the result. Gandiva is a greedy approach which is fast, but it has a poor quality. POP4 has similar quality per time trade-off, but it is 1.x slower than DD. POP16 is also a type of POP4, but it has 16 subproblems, so it computes faster, but it has a slower solution quality because the subproblem splitting limits cross-step assignment choices. DD versus DD star. DD star is an idealized approach which appears 3.3x faster than DD. It assumes perfect dynamic scheduling, while DD measures end-to-end time. DD is slower than DD star in practice because DD measures end-to-end time, which includes solving and compilation time, but DD star only counts core solving. Parallel implementation overhead is there in DD, and static assignment of subproblems causes delays in DD. Our next case study is traffic engineering. Traffic in our daily life is the movement and flow of people and vehicles on the road. Here, the traffic engineering is to decide how the data flows through a network. What does traffic engineering do? It routes flows across multiple possible network paths, it balances load across links, and it prevents any bottleneck, and it ensures quality of service for applications, which ensures minimum latency and throughput, and it also adjusts dynamically based on changing traffic patterns. From this image, we can see that the network is crowded and congested. So any bottleneck forming in a network can cause change in latency and throughput. So we must avoid congestion and make the best use of available bandwidth. Coming to formula variables, let x of u comma v denote the amount of flow from data center pair s comma t assigned to a network link uv, where s and t are the source and destination data centers respectively. Here p of s comma t denotes the set of all nodes from the path s to t. A node v has its inflow from the pair of s comma t as sigma over x of ub from all the wedges between p of s comma t, and outflow as the sigma of x of u comma v from all the edges between s and t. Here our objective is to maximize the total flow between all the node pairs, which is expressed as this resource constraints. For each link u comma v, the cumulative flow from all the node pairs traversing it must not exceed its link capacity c of u comma v, which is given by this equation. The demand constraints. For each node pair s comma t, the total flow allocated cannot exceed the total demand. Additionally, for all nodes other than s and t, the inflow and outflow must be equal, ensuring there is no black hole along the paths. It is given by the equation. There is another variant called minimizing max link utilization. It aims to distribute the traffic evenly across the links to avoid overloading of any single link. Utilization of the link is the ratio of total flow assigned to the link capacity. In practice, it cannot be greater than 1. This variant has variables and constraint as same as the before, but the objective here is to minimize the max link utilization across the network, which is given by the equation. How can DD be applied to solve traffic engineering? We have seen that the traffic engineering problem aligns with the separable structure of DD. The objectives are expressed either as sum over per demand utilities or as a maximum over per link utilities, and a linear constraints are applied to each demand and each link. Therefore, we can decompose the problem into E per link allocations and V square per demand allocations for parallelism. In practice, due to large overhead of maintaining these V square per demand subproblems, we group these subproblems by this and we reduce the number of subproblems to V instead of V square. DD versus others for min-max link utilization. As we can see from the graph, DD attains a maximum link utilization of 1.67 within 10 seconds and 1.75 within 5 seconds. It is a falling trend. Coming to other solvers like the exact solution, it achieves 1.63 maximum link utilization at 35 seconds, which is better than the optimum but slower than DD. Pining takes 42.5 seconds, which is slower than the DD. It has overhead when the top flow changes. Coming to the pop family, if it has more parallelism, it is faster but it has worse quality. DD has approximately pop 16 runtime because of its similarization assumption of the parallelism. TLML attains a maximum utilization of 1.74 within 0.3 seconds. It is extremely fast even than DD because of its domain custom machine learning algorithms. DD versus others to maximize the total flow. As we can see from the graph, DD satisfies 90.8% demand in 30 seconds, 92% demand is satisfied in 60 seconds. It has best speed quality trade-off. Other solvers like DD star has 8% error when compared to DD. And coming to the POP family, when there is more parallelism, the computation time is less, but the error rate increases and the quality decreases. Pining takes 87.3% in 149 seconds due to its sequential computation, and Teal attains 89% just within 1 second. It is extremely fast because of its domain custom ML.
Now let's take a look at another case study, load balancing. Whenever some servers become overloaded, the system reassigns shards to restore balance. However, this problem is non-convex and integer constant, so it is NP hard to solve. That's where DD provides high quality empirical solutions despite its non-convexity nature, and our objective function is to minimize the shard movement. Here we can see the objective function, resource constraints and variables and domain constraints too. The variables decide which shard goes to which server, and constraints ensure each shard is assigned exactly once and no server exceeds its capacity. Now, DD can be applied here because the load balancing problem has what's called a separable structure. The objective function can be broken into smaller independent parts for each shard and each server, so DD can decompose the global problem into per server and per shard allocations, making it much faster to solve. Data shards are small portions of a large data set stored separately across multiple servers. Load balancing then decides how these shards are distributed so no server gets overloaded. DD achieved 20.1 shard moves in just 15 seconds. Even within its faster 5-second mode, DD still performed with 25.4 moves, and the optimal was at 20.9, and which it took 4,820 seconds to compute because it's NP hard. So we can see DD is very efficient from this graph. Now let's talk about robustness of DD, how well it performs under chaotic real world conditions. In our evaluation, we tested DD against real world uncertainties, things like network irregularities, sudden traffic spikes, and resource failures. Specifically, under granularity changes, POP collapses by 12.3%, but DD remains constant, like it's just 2.1% drop. And in fluctuation test, ML based TL solver fails by 12.8% drop, but DD remained stable by just 1.3 to 3.5% change. And in redistribution, when traffic isn't heavily tailed, pinning failed by 8.3% drop, but DD is stable. Granularity. Granularity here means how interchangeable the resources are. The test examined how solvers perform when some network links become critical and cannot be easily swapped. We altered the topology of the network so that certain links which are more important, creating non-granular condition, which breaks solvers like POP that rely on uniformity. As shown in graph, DD remained pretty constant, but POP has fallen very much. Temporal fluctuations. Next, we looked at random unpredictable noise in demand, simulating sudden traffic surges or dips. We added noise that scaled up to 20 times the normal traffic, which is highly chaotic. This kind of test is especially tough for machine learning based solvers like TL because they are trained only on normal and predictable data. But we can observe that DD's output is pretty stable. Spatial redistribution. Spatial redistribution means changing where traffic comes from, shifting from a few big sources to many small, even ones. This test breaks shortcuts like pinning, which focuses only on the top 10% of the traffic. When the traffic was evenly spread, pinning performance dropped by 8.3%, but DD stayed steadily and kept delivering top results. Link failures. The purpose of this test is whether a solver can recompute its network flow allocation after a network topology suddenly changes. This test was different from the other three which we discussed before. The goal wasn't to show that a competitor is failing, but to show that DD remains stable and functional even when the network itself breaks. Micro benchmarks. This section focuses on how DD's key architectural components impact its overall performance. Here we look at three aspects. Does DD actually get faster with more cores? How quickly it find good solutions? And is its EDMM approach really better than traditional methods? CPU code scaling. The goal here is to verify if DD's parallel design truly works or not. The test was run on 1, 4, 16 and 64 CPU cores, and the graph beside shows the performance scales with more cores. We can see that as we increase the number of cores, DD achieves significant speed up, confirming that it efficiently utilizes available hardware resources instead of bottlenecking at a single process. Next, we evaluated the convergence rate. How quickly DD reaches a high quality solution and how the initialization method affects that speed. Three different starting points were tested here. There are the default warm start and the TL initialization and the naive initialization. The results show that DD converges better than the warm start, proving that its ability to leverage prior knowledge efficiently. At last, DD's ADMM based approach was compared against two standard monolithic techniques, the augmented Lagrangian and the penalty method. While the other methods solve the problem jointly and become computationally heavy, DD breaks it into smaller independent and sub problems which can run in parallel. And we can see that how fastly it has achieved the satisfied demand than augmented Lagrangian and penalty. This makes it both faster and more scalable, demonstrating why ADMM gives DD its performance edge. Industrial relevance. This DD framework is itself recent and presented as a research prototype recently in June 2025. But its underlying principles ADMM have proven effective in real-world systems. FinTech Alipay's PDS system and cloud and data center resource allocation are few examples of these ADMM based distributed algorithms. This paper identifies that majority of real-world resource allocation problems possesses an inherent separable structure. This key insight enables the DD framework to systematically decouple and decompose constraints into independent parallel subproblems. And this DD has also been implemented as a push button Python package through an extensive evaluation to signify its uh, improving scalability while achieving solution quality that close approximates exact solutions.